Point two stars at each other, dead center, no glancing angle, no near miss, a perfect head-on, and let them close the gap. Most people picture the obvious thing, the biggest explosion imaginable, two suns detonating in a flash that outshines a galaxy. And sometimes that is exactly what happens. But sometimes the same head-on collision does the opposite. It quietly builds a brand new star that looks younger and burns brighter than either of the two that died to make it. Same setup, same head-on, opposite endings. The entire outcome hinges on a single number, and if you get that number wrong, you'll predict a nursery when the answer is a slaughter. So let's actually run the crash, slowly, from the first contact to the last, and find out which one you get and why. Before any of that though, you have to appreciate how staggeringly unlikely this event is in the first place, because it tells you where you have to go to see one. Space is not crowded. It is the emptiest thing there is. Our sun's nearest neighbor, Proxima Centauri, is about 4 light-years away. And to picture what that means, shrink the sun down to the size of a single grain of sand. On that scale, the next grain of sand isn't across the room. It's roughly 6 kilometers away. An entire city of empty space between two specks. Stars in our neighborhood are separated by tens of millions of times their own width. Firing one at another and scoring a direct hit is less like a shootout and more like flicking 2 grains of sand from opposite ends of a continent and expecting them to strike head-on in the dark. It's so unlikely that even when entire galaxies smash together, the stars inside them almost never touch. In a few billion years, our Milky Way is going to collide with the Andromeda Galaxy, a genuine full-speed galactic pileup involving 1 trillion stars. And the number of stars expected to physically hit each other in that titanic wreck is, as far as we can tell, essentially 0. The two galaxies will glide straight through one another like 2 swarms of gnats crossing paths, each star sailing through gaps millions of times wider than itself. If galaxies colliding can't force a stellar collision, then to actually get 2 stars to meet head-on, you need something far denser than a galaxy. You need a genuine crowd. Our own sun, for the record, will never experience any of this. It lives in the thin suburbs of the galaxy, and it will end its life quietly and alone, swelling into a red giant, sloughing off its outer layers, and settling into retirement as a slowly cooling white dwarf, never once touching another star. The collisions we're chasing don't happen to typical stars in typical places. To find one, you have to go where stars are forced unnaturally close together, and the universe does build crowds. Deep in the hearts of globular clusters, ancient, tightly bound swarms of hundreds of thousands of stars, the core can get packed so densely that stars are separated by a fraction of a light year instead of several. In places like that, near misses and outright collisions stop being unthinkable and start being routine. Over the lifetime of a single dense cluster, several hundred stars can physically run into one another. The other great meat grinder is the region right around a supermassive black hole at the center of a galaxy, where stars are crammed together and whipped to enormous speeds. Hold on to those 2 locations because, as you're about to see, they produce completely different disasters from the exact same collision. That difference is the whole story. How a cluster builds such a lethal core is a slow gravitational sorting process. Over billions of years, the heaviest stars sink toward the center while the lightest drift outward, and the core keeps contracting on itself, a runaway that astronomers bluntly call core collapse. The center grows denser and denser until the stars there are stacked hundreds of times more tightly than in the sun's neighborhood, and what was unthinkable in open space becomes just a matter of waiting. Collision in these places isn't an accident, it's the destination the whole system is quietly falling toward. Now, to predict a crash, you have to know what you're actually crashing. And here's the first thing people get wrong. A star is not a solid ball. It's not a cannonball, and it won't behave like one. A star is a sphere of plasma, superheated gas with the electrons stripped off, held together by its own gravity, and it is wildly lopsided in density. The sun's core is crushed to more than 100 times the density of water, but its outer layers thin out into something closer to a vacuum. The visible surface isn't a surface at all. It's just the depth where the gas finally gets thick enough to be opaque. So when two of these things meet, you are not clacking two marbles together. You are colliding two enormous, fuzzy-edged balls of gas that can flow into each other, pour through each other, and splash. That single fact that a star is fluid, not solid, is why the speed of the collision decides everything. Because every ball of gas has an internal speed limit, the speed of sound inside it, the pace at which a pressure wave, a piece of news, can travel through the material. In a star, that internal sound speed runs to hundreds of kilometers per second, and the rule of any collision between fluids is brutally simple. If you slam them together slower than that internal speed, the gas has time to react, to shove back, to redistribute the energy gently. If you slam them together much faster, nothing can react in time. The material simply gets shocked, crushed, and blown apart before it even knows what hit it. So the question isn't really what happens when two stars collide. The real question is, how fast were they going compared to the sound inside them? Everything follows from that. Let's take the gentle case first. The collision in the crowded core of a globular cluster. Stars there drift into each other at something like 10 kilometers per second. That sounds enormous, and by everyday standards, it's absurd. But it is far slower than the hundreds of kilometers per second of sound inside the stars. So this head-on is a slow-motion event in the only sense that matters. The two stars don't shatter. They wade into one another. The outer layers meet first and begin to merge. A shock forms and heats the gas, and the two dense cores plunge together through the shared envelope. Some material gets flung outward hard enough to escape entirely. Simulations of two equal sun-like stars hitting head-on show them losing only a few percent of their combined mass, maybe 4 to 8%, sprayed off into the cluster. And the rest? The rest stays. It sloshes, it churns, it violently mixes. And then, over hours and days, gravity pulls the whole hot, bloated, wildly spinning mess back into a single sphere. Two stars went in. One star comes out, heavier, hotter, and thoroughly stirred. That merged star is where the story takes its first real twist because of what it looks like afterward. It looks young. When a star fuses hydrogen, it slowly changes color and brightness as it ages, so astronomers can read a cluster of stars almost like tree rings and say, these are all ancient. But sprinkled through those ancient clusters are oddball stars that are hotter, bluer, and brighter than they have any right to be. Stars that appear to be far younger than everything around them. They're called blue stragglers, first spotted back in 1953 in the cluster M3. And for decades, they were a genuine puzzle. How do you get a young star in a swarm where everything formed at the same ancient time? The answer, in many cases, is exactly the collision we just ran. Fuse two old, faded stars into one, and you get a single, more massive star with a fresh supply of fuel dragged into its core. A star that has, in effect, cheated its own age. Every old cluster is quietly hiding these fossils of past head-on collisions. Stars that should be elderly and instead blaze like the newly formed. That's the answer in the gentle case. A head-on collision doesn't destroy a star, it rejuvenates one. Though rejuvenates hides a complication the simulations kept slamming into. When two stars merge, they don't just add their mass, they add their motion, and all that leftover spin has to go somewhere. The merged star can end up rotating so fast it's on the verge of flinging itself apart, bulging grotesquely at the equator and shedding streamers of gas into a disk around itself before it finally calms down. The making of a blue straggler isn't a tidy fusion. It's a frantic, off-balance spin-up that the new star has to survive before it can settle into looking deceptively young. And this isn't only theory pulled from computer models. In 2008, we watched a version of it unfold live. A faint object in the constellation Scorpius, catalogued as V1309 Scorpii, had been quietly monitored for years, long enough for astronomers to notice its light pulsing with a rhythm that was steadily speeding up. It was two stars in a contact binary, already touching, spiraling inexorably together. Then, in September of that year, it erupted, brightening by a factor of thousands and flaring into what's called a luminous red nova. But instead of getting hotter the way an ordinary explosion would, it turned redder and cooler by the day and wrapped itself in a shroud of freshly made dust. We had caught two stars in the literal act of becoming one. The merger, predicted for decades, finally witnessed from the first flicker to the last. The head-on merger is not a hypothesis. We have the footage. But now, change that single number, the speed, and watch the entire outcome invert. Take those same two ordinary stars and stage the collision not in a quiet cluster, but in the savage traffic around a supermassive black hole. There, a star's speed isn't 10 kilometers per second. The black hole's gravity whips stars up to hundreds, even thousands of kilometers per second, now comparable to, or faster than, the sound speed inside the stars themselves. Run the head-on at that speed, and the gentle merger is gone. The gas can't respond fast enough. Instead of pooling together, the two stars punch into each other and generate a shock so violent it can strip, gut, and disrupt them, blasting stellar material out in a hot, expanding cloud rather than settling it into a new star. Astronomers actually invoke this to explain a mystery at the center of our own galaxy, a curious shortage of certain red giant stars, which may be getting battered apart in exactly these high-speed collisions. Same two stars, same perfectly head-on geometry. One location builds a star, the other shreds it. The only thing that changed was how fast they were moving. It's worth dwelling on how different those two shocks really are. In the slow cluster merger, the gas is nudged and given time to respond. In the high-speed version, beside a black hole, the two stars meet with so much kinetic energy that the impact front blazes to temperatures beyond anything in either star's core. And material is flung outward faster than the star's own gravity can ever call it back. A slow head-on adds two stars together. A fast head-on is closer to a demolition, converting two orderly stars into an expanding, cooling cloud that the galaxy simply swallows. And the line between those two fates isn't a gradient. It's a hard threshold set by whether the closing speed beats the speed of sound in the gas. And almost nothing else. So that's ordinary stars. And honestly, they're the tame version. Because a star doesn't have to be a living, hydrogen-burning ball of gas. Some of the things we collide are the dead ones, the compact corpses stars leave behind. And when those hit head-on, the physics goes from dramatic to apocalyptic. Here's where the collision stops making stars and starts making the elements. Take a white dwarf, the exposed Earth-sized core of a burnt-out star, cooling and inert, but with the mass of a whole sun crammed into a ball the size of our planet. A teaspoon of it weighs tons. It is packed almost as tightly as matter can be while still resisting collapse. Now smash two of those together head-on. The impact compresses the carbon and oxygen inside past a critical threshold. The material ignites all at once, and the entire object detonates in a runaway thermonuclear explosion, a Type 1a supernova, bright enough to be seen billions of light years away, hurling the fused wreckage of both stars across space. Most such supernovae are thought to build toward detonation slowly, with one white dwarf siphoning gas off a companion over ages, but a genuine head-on smash between two of them is a separate, far more sudden trigger. And in the crushed cores of the densest clusters, where such direct hits are actually possible, astronomers suspect a fraction of these blasts are literally collisions rather than slow thefts. And these particular explosions do something else remarkable. Because that detonation threshold is nearly identical every time, Type 1a supernovae flare to almost exactly the same true brightness wherever in the universe they happen. That consistency turns them into cosmic measuring sticks. Compare how bright one truly is to how bright it appears from Earth, and you can read off its distance across billions of light years. It was precisely these exploding dead stars that in the late 1990s revealed that the universe isn't merely expanding but accelerating, the discovery that dragged dark energy into physics and rewrote our picture of where everything is headed. A collision between two burnt-out stars didn't just forge elements, it handed us the ruler we used to measure the fate of the cosmos. And then there are the neutron stars. And this is the collision that, in 2017, humanity finally got to witness. A neutron star is what's left when a massive star's core collapses so hard that protons and electrons are crushed into neutrons, an object with more mass than our sun, packed into a sphere the size of a city, maybe 20 kilometers across. Its density is the density of an atomic nucleus. A sugar cube-sized piece would weigh about as much as all of humanity combined. Two of these, locked in orbit, spiral closer and closer over millions of years, and finally slam together in the most extreme head-on collision the universe permits. The final act takes only seconds, and it is almost beyond describing. In the last moments, the two neutron stars are whirling around each other hundreds of times every second, at a sizable fraction of the speed of light, wrenching space and time so hard that they send waves rippling outward across the universe. Those gravitational waves haul energy away, so the orbit tightens, the whirl accelerates, and the pitch of the whole system rises, a climbing chirp that ends the instant the two stars touch and are ripped open. What's left behind may briefly be a single, monstrous, overmassive neutron star, or it may collapse then and there into a black hole. Either way, the collision has already done its real work in the debris hurled out during those final milliseconds. On the 17th of August, 2017, we felt one happen. The LIGO and Virgo detectors picked up a tremor in the fabric of space-time itself, gravitational waves from two neutron stars merging in a galaxy called NGC 4993, well over 100 million light-years away. To register that ripple at all, the detectors had to sense their 4-kilometer arms stretch and squeeze by less than 1,000th of the width of a single proton. And they did. About 1.7 seconds later, space telescopes caught a burst of gamma rays from the same spot. And 11 hours after that, telescopes on the ground found the visible afterglow, a new point of light that astronomers had been predicting on paper for decades but had never once seen. It's called a kilonova. For the first time, we had watched the same cosmic event through gravity and through light at once. And what that light revealed is the part that should genuinely stop you. When those two neutron stars tore into each other, the collision flooded the surrounding space with free neutrons at unimaginable density. And in a few seconds, those neutrons jammed themselves onto atomic nuclei faster than the nuclei could decay, a process that forges the heaviest elements in existence. That single merger is estimated to have manufactured on the order of 16,000 times the mass of the Earth in heavy elements. And among that debris, according to the measurements, were several Earth masses worth of gold and platinum. Real gold. The same element, created in the instant two dead stars collided head-on. We now think that neutron star collisions like this one are responsible for roughly half of every element heavier than iron in the universe. Collisions this violent are rare. A galaxy like ours may host only a handful of neutron star mergers per million years, yet stretched across cosmic time and billions of galaxies, those isolated flashes accumulate, one spray of debris at a time, until they add up to a whole swath of the periodic table. Sit with what that means, because it collapses the whole distance between a cosmic catastrophe and your own hand. The gold in a wedding ring, the platinum in a phone, the heavy metals scattered through your own body. A real portion of it was very likely born not in a calm star, not in a gentle furnace, but in the split-second violence of two stellar corpses hitting each other dead on, somewhere billions of years before the Earth existed. The debris drifted for eons, seeded a cloud of gas, and some of it ended up here as jewelry and blood and rock. Head-on stellar collisions aren't a distant curiosity. They're part of the supply chain that built us. So, what happens when two stars collide head-on? There is no single answer, and that turns out to be the most interesting fact of all. It is not one event, it's a machine, and what comes out depends entirely on who's colliding and how fast. Slow in a crowded cluster, and two dying stars merge into one that looks young enough to fool astronomers. Fast beside a black hole, and the very same stars are ripped to shreds. Two white dwarfs, and you get a supernova bright enough to outshine a galaxy. Two neutron stars, and you get gravitational waves, a flash of gamma rays, and a spray of freshly minted gold. two stars meet head-on. The universe decides what to build from the wreckage: a new sun, an explosion, or the atoms in your ring. And every time, the answer was hiding in a single number: how fast they were falling.